Hello everyone, my name is Igor Hagar. I'm from the Project Management Office from the RADNEXT project. And we just briefly share my slides so you can um, so we can start this webinar. Up. This webinar is organized by RADNEXT. I don't know if it's your first time listening or if you're not familiar with RADNEXT. It's a European funded project, and the main goal is to enhance the accessibility to accelerator infrastructure, especially for radiation effects testing. So here we have the radiation facilities webinar, where the main focus is to discuss the present and future of radiation facilities worldwide and to discuss the challenge of using them for radiation testing, so single-event effects and different effects in electronics device. So this webinar series started in 2022, so we had many webinars. So the last one was in December 2022, so we had a break in 2023. And as you see, we had speakers from Japan, from the US, from Australia, so everyone everywhere in the world discussing how we can improve facilities to adapt and enhance the single-event effects testing methodologies. So if you're not able to attend to these webinars, you are invited to follow and to check all the videos because these webinars are recorded and available on our YouTube channel. So here you can just scan this QR code or look for RADNEXT channel. And today we are here for another webinar, and we have the pleasure to have here connected the Dr. Michael Sivertz from the NASA Space Radiation Laboratory, where he will present the challenges and the advantages of using high energy ions for SE testing. And so just to give more introduction to the project, if you want to know more about our activities or about the structure of this RADNEXT project, you can find our website. So you can find information of the different work package like networking activities or research topics, and also very importantly, the transnational access to beam time. We also have some blogs, so we have some posts or publications on the events we organize and different opportunities in the network. So we also invite you to check our website. We are also very active on social media. So if you use LinkedIn, we also very often we post about our call for proposals for beam time and the different events that we organize. And also users sometimes they post and tag us. So if you want to be up to date to the different testing and different events and opportunities, you can just follow us on LinkedIn. And one of the core activities of the RADNEXT project is to provide beam time through transnational access to radiation facilities within the network. So the network is composed of different facilities in Europe and Canada. And so we have more than 6,000 beam time to provide to users. So more information on these requirements you can find on the website. But beam time is awarded by RADNEXT, founded by the EU. And you can see here that we reached over 2,500 hours already. So the next call will be open in May. So put in your agenda and prepare a nice project and proposal for the next call. As a European project, we also are engaged on providing the radiation report, the testing report online, public, on the Zinode repository. So here we have all the transnational access summary report. It's not a complete report, but we have the main objective of the experiment and some data analysis. And also we publish is all the preprints of our publications, so research papers. And just to mention one event that we are organizing every year is the GRADNEXT, but today this year we just rebranded to GB RADNEXT because it's gonna take place in UK. And for more information, you can also check on this QR code. We have more information in the eco page of the event. So thank you very much. And now I will just give the floor to Dr. Mike Sivertz.
Thank you very much. I'm going to try to display this as a slideshow and share that. Okay, we'll do it like this. Can you see the presentation?
Yes.
Okay. I'm not really sure who my audience is, so bear with me if I get repetitive or talk at a level that may seem wrong to you, but I'd like to start with a brief discussion about cosmic rays. Then I will tell you about some of the physics considerations to use when designing experiments for high energy heavy ion electronics testing. And then I'll spend a long time discussing the logistical considerations, how best to conduct those tests at a facility like the NASA Space Radiation Laboratory. And lastly, end up with a brief advertisement for future directions in high energy electronic testing at BNL. So the galactic cosmic ray spectrum is made up of course, primarily protons, 90% protons, with 8 or 9% helium, making up nearly all of the rest, with only 1% of the ions being between carbon and iron, with some of the very heaviest ions being less than a fraction of a percent. And yet, the work that's done at the NASA Space Radiation Laboratory is about half radiobiology. It was designed as a radiobiology facility by NASA. And the radiobiology is interested in protons to iron. They do effectively zero testing for any elements heavier than iron. On the other hand, the electronics testing rarely tests with anything lighter than iron. And they tend to go from iron up. The spectrum of galactic cosmic rays peaks in the region from 300 to 1,000 MeV per nucleon, with a very broad peak. And the spectrum is nearly independent of the ion species. The peak is in the neighborhood of 300 to 1,000 MeV per nucleon for all ions. The red line that you can see here represents the upper limit of the energy range at the NASA Space Radiation Laboratory. So we can simulate the ions with kinetic energies less than that value. And that represents just over half of the entire spectrum of galactic cosmic rays. There are plans to extend the energy range for a future electronic testing facility here at Brookhaven. The sources of galactic cosmic rays depend, of course, on the species. Protons, helium, and a little bit of lithium is produced primarily left over from the Big Bang, it's believed. The intermediate atomic numbers are produced, it's believed, through supernova explosions that produce everything up to iron, cobalt, and nickel, and spread those products throughout the galaxies. Currently, it's believed that the things heavier than that are produced in neutron star coalescences. So, down to the issues of testing. What are the important physics issues for electronics testing? There are two effects produced when a charged heavy ion goes through materials. The predominant effect is ionization. This charged nucleus will interact with electrons, will strip electrons off the atoms in the material, and that represents more than 99% of the interactions that occur. Additionally, there can be nuclear scattering when the heavy ion strikes the nucleus in the material that's passing through directly. And this can produce something called displacement damage, where there are actual structural changes to the material that is passed through. The ionization energy loss is described by a Bragg curve. I'll show some images of measured Bragg curves as measured at the NASA Space Radiation Laboratory for different ions. And I'll talk about the parameter LET for linear energy transfer, which is essentially the dEdx, the energy loss per unit length of the ion as it passes through matter. And lastly, I'll talk about how that energy is deposited in the sample, how uniformly it's distributed for different kinetic energies. And I'll end with a personal bias about effective LETs. So when a heavy ion, like a 1 GeV per nucleon iron nucleus passes through matter, it produces 99.9% of all its energy losses is through ionization, produces electrons at a very high density. Contrary, the nuclear scattering that can sometimes occur, although it is a small fraction of the cross-section, the total cross-section, it can result in a very large energy loss and change the trajectory of the incoming projectile and produce ionizing secondary particles that also have a long residual range themselves. This kind of interaction is the only method for neutron energy loss. And this displacement damage can recover through annealing by heating of a material, or even through self-annealing for certain materials that have a low transition temperature. This is an image of a Bragg curve that was measured at the NASA Space Radiation Laboratory by taking protons of 205 MeV and degrading them with polyethylene, high-density polyethylene. We measure the energy loss, the ionization produced in an ion chamber upstream of the degrader material and downstream of the degrader material. And we take the ratio of those two and define the undegraded beam as having a ratio of 1. And then as the degrader material is used to slow down the beam, the energy loss increases until it reaches a peak just before the beam is stopped, something like 55 keV for a proton. And that describes the Bragg peak. the range of that ion is given as the place where the Bragg peak falls off. There are some religious arguments about whether that should be halfway off the Bragg peak or 2/3 or 3/4 of the way off the Bragg peak. I will ignore that for this discussion. And then, of course, there is no energy loss beyond the Bragg peak for protons because they stop, because there's nothing left to carry the energy. For a comparable carbon beam, this is the same measurement for a 293 MeV per nucleon carbon beam. And it has very similar shape, rises to a peak just before stopping. But you can see that there is a tail to this Bragg curve, and that is because when the carbon beam is being degraded in the polyethylene, some of those carbon ions will fragment, turn into protons or alphas, each traveling with nearly the same velocity as the carbon ions themselves, and having therefore a much longer range. So the tail of this distribution is an indication of how much of the carbon beam has been fragmented along the way. When we do the same thing with an iron beam, this shows a nearly 1 GeV per nucleon iron beam. The Bragg curve drops quite rapidly initially. And the Bragg peak itself barely manages to get back to the energy level of the entrance LET, with a very long and substantial tail due to all the fragments, all the secondaries that are produced when iron passes through the polyethylene. So there are the dropping of the Bragg curve initially is a product of the fact that when the iron fragments, when the iron turns into lighter ions, protons, alphas, and lower mass ions, the sum of the LET of all those ions can never equal or exceed the LET of the iron itself. So although each of the ions is increasing its LET as it's slowing down, so each of those iron ions and all of the fragments have an LET that's increasing. The dominant effect, as you can see, is a dropping of LET as the iron itself fragments into light ions. When operating at a lower energy, the previous plot for iron was at 963 MeV per nucleon. For a lower energy heavy ion, like this 273 MeV per nucleon xenon curve, the fragmentation can be seen to be less. There's less nuclear interactions at lower energies, so the beam stays less. It has less fragments, less tail to the Bragg curve itself. So what is of interest to electronics testers? Here I've imagined a device under test that perhaps it has a lid, an aluminum or copper or ceramic lid, a central silicon region, the active layer, and the LET of interest will be the LET where the active layer is present in the ion beam. This This particular Bragg curve was made for 170 MeV per nucleon gold ions in silicon. So obviously, if you have an active layer that has a non-zero thickness, then there will be an entrance LET and an exit LET. And if you are working on or near the Bragg peak, the uncertainty in the LET that you are using to test your device can be quite substantial. It's for that reason that at the NASA Space Radiation Laboratory, we recommend, whenever possible, that the parts be tested on the plateau with the highest kinetic energy that is achievable for delivering the LET requested. The further you go up the Bragg peak, or beyond the Bragg peak, of course, the greater the uncertainty in the LET that you're testing with. For some testers don't know the material that they're testing. They don't know what the material is. They don't know the thickness of the different layers. This might be for various reasons. Some people just have not taken the time to measure it. Other people come with proprietary devices that they're testing for a customer, and the customer doesn't want to tell them what's in their part or the thickness of each layer. And so they are a little bit at a loss for the best way to do the testing. And some testers have addressed that problem by this technique called the variable depth Bragg peak, where essentially they start by, they begin with enough degrader to actually stop the beam before it hits their active layer. And then they take out degrader and they see when they start to get upsets. And they assume that that is caused when the Bragg peak has been placed in the active layer or the layer of interest of their part. And then they continue to remove degrader, moving the Bragg peak beyond their active layer and testing at lower LETs as they work their way backwards off the Bragg peak. And in this way that they can actually achieve it's like a tomographic map of their part. They can scan through and discover the thicknesses and the material composition of their part. With a single beam and different degrader settings, you can test exactly what the part is made of by seeing at what degrader thicknesses the upsets occur. For some of the radiobiologists, we have a technique called a spread out Bragg peak, where we take a single pristine Bragg peak and use a spinning wheel with various thicknesses of degrader material to sum up, in this case, 50 individual Bragg peaks with different weightings in order to produce effectively a spread out Bragg peak that is the width of the spinning wheel. This is designed for radiation therapy, where the depth of the tumor or the depth of the spot that you want to irradiate is large compared to the width of the Bragg peak itself. You might have a tumor that is 2 centimeters in diameter. And so you would design a spinning wheel that could produce a spread out Bragg peak with a a uniform dose distribution across the tumor, falling off at one side where there is no Bragg peak placed, and falling off on the far side by the stopping beam. That has been used regularly to irradiate tumors in biological samples here at NSRL. A question that has been posed often is people come and say, I want to test, or I have a benchmark to hit. I have to hit an LET of 37 on this part, 37 MeV per milligram per square centimeter, a typical request. And we might ask then, well, what ion do you want to produce that LET with? And oftentimes they don't know or they don't care. But it matters. For instance, I've got an example here of 4 different ions at 4 different kinetic energies that all have the same LET, an LET of 14 MeV per milligram per square centimeter. And you can achieve that with an argon atom at 4.8 MeV per nucleon. And the charge radius, i.e. the radius containing 50% of the total ionization, is only 63 nanometers for that ion. Similarly, krypton at 38.5 MeV per nucleon has the same LET, but that ionization is distributed across a radius of 247 nanometers. Whereas tantalum at 310 MeV per nucleon has the same LET, but distributing that charge over a distance greater than a micron. So it's clear that when the ionization is spread over volumes that are of such vastly different scale, they will have very different effects. So it is a consideration to be taken into account. Different kinetic energies have different charge densities. So it's not merely the LET that matters, that must be considered when planning your test. You also have to know exactly what the effect of that LET is going to have on the part. And this plot just shows for a given LET, different ways of achieving it with ions of different kinetic energies. Lastly, a pet peeve of mine, I have people come in and ask for effective LETs that they achieve by rotating their part. Of course, LET is energy deposit per unit length, and that doesn't change when a part is rotated. The deposited energy can change, but not the LET. For example, a part that has a thickness T will have a total energy deposited that is just dEdx times T. And rotating it, you can change that deposited energy by changing the effective path length through that part by 1 over cos theta. I was working with a CCD camera where the pixel size of that camera was 10 microns by 10 microns. But because it wanted to have good infrared sensitivity, the depth of the CCD pixels was 300 microns. So the total energy deposited, if for a normally incident cosmic ray, would then be dEdx times the 300 micron length of that pixel. And certainly rotating that pixel then does not increase the deposited energy. It actually drops it quite a bit because you're no longer passing through the length of the pixel itself. So I'd prefer not to use the term effective LET, but rather speak about the deposited energy itself. Okay, now on to some nuts and bolts about the NASA Space Radiation Laboratory itself. I'll begin by talking about the access method. This is just showing the entryway to our target room. We have a big red crash button that all accesses begin by disabling beam by pressing the crash button. And once beam is disabled, we perform an iris scan, which identifies people making an access and connects that person with the training database to verify that they have all the trainings required to enter the target room. If their training is all up to date, it will unlock a key from this key tree here. And that key tree has an RFID tag in it. And when that key is removed, the door to the target room will open. You can walk through the door to that target room carrying your key. There's an infrared people counter that will count the number of people entering and the number of keys entering with the RFID tag reader. There has to be one person and one key at a time. If it sees anything that it doesn't like or is confusing to it, it drops the interlocks and requires a sweep to verify that the target room is empty before beam can be re-enabled. We have found this to be fairly quick from getting access to the target room, as opposed to some similar facilities that have for instance, a sliding plug door that might take 5 or 10 minutes to open the door, moving 6 feet of concrete. The total time between beam off, going through the access protocol, entering the target room, doing the work and coming back out is either from 3 to 5 minutes, plus whatever time it takes to get the work done inside. And we found this works quite well, quick and easy. One of the most effective tools that we have is a beam camera. This produces an image for us of the beam spot on a spill by spill basis. The beam spot at the NASA Space Radiation Laboratory can be quite large. We typically operate with a beam spot that is 20 centimeters by 20 centimeters. You can see the outer fiducial marks here are separated by 20 centimeters. And we are able to produce a radiation field that is uniform. We typically quote a 2 to 3% RMS variation across that radiation field. And the camera allows us to monitor that on a spill by spill basis. We normally operate it with false color. The bright colors are showing where the radiation field is extra strong around the edges. That's a figment of the magnetic focusing, the octopole focusing that we use to produce the large flat beam profile. On the right, you can see there's a circuit board in place. You can see the various components distributed across the circuit board. And on the bottom here is a large vise used to hold the circuit board. That looks like a bismuth beam to me. And the top right corner shows a slice across the image giving you the beam profile with the hot sides and large, flat, uniform radiation field across the center. We also sometimes we run with a very large beam. We can run with a 60 by 60 square centimeter beam. And when we do that, the camera no longer fits the beam, and we have to use a large pixel chamber. We have a 80 by 80 square centimeter pixel chamber with 1,024 pixels. This is an image of the beam in that device. And again, you can see the ears of the beam. There are no ears on the bottom because that's truncated by the rail system that holds the ion chamber. But again, the large flat beam distribution in the middle. The pixels are 1 inch squared, and because it's a fairly thick ion chamber, it makes for great sensitivity. Additionally, upstream, we have a segmented wire ion chamber that gives us a two-dimensional profile. There are 32 wires in the horizontal and 32 wires in the vertical that can give us a spill by spill look at a cross-section across the beam. And it has fast readout. So the same device provides the time structure of the beam. This is showing for a gold ion, the beam delivery, where the spill comes out over a 400 millisecond period. The readout is performed for every millisecond. You can see there is 60 hertz ripple on the beam intensity. We have some ideas about how to smooth that out, but they are still in the development stage. For some of the work we do, electronics testing, when we're looking at sensitive parts, for instance, today we are going to be working with 1,000 ions per square centimeter per spill. And neither the camera nor the ion chamber is very good at recording such low fluxes. And so in order to assure ourselves that we still have good beam uniformity, we built these edge counters, we call them. They're just 4 plastic scintillators that can be extended into the halo of the beam. And they see every ion. They're used to count every ion. And by adjusting the beam steering to balance the top and bottom and the left and right scintillators, we can continue to operate with the uniform radiation field down to the single digit of ions per square centimeter. We have also found that it's helpful for the laboratory itself to maintain a set of sample holders and breadboards. We mount all our work on one of these optical bench type breadboards. It's an aluminum breadboard with threaded holes on a 1 inch pattern. And we provide these to the researchers outside of the target room, so that perhaps on the day before their scheduled beam time, they can set up all their equipment on that breadboard, make sure that everything is stable, everything works. They can talk to all their parts, Then we just roll the cart into the target room, transfer that breadboard onto the beamline, and in a very short period of time, get operating. We have a wide variety of sample holders. We've chosen to, we recommend to users that they make use of those sample holders so that they are not bringing their own sample holders, which then get activated, and they have to leave them here. We don't want to be collecting sample holders. Typically, the sample holders that people bring are have heavy metals in them. They have they're made of things that are going to get activated and stay activated for a long time. So we much prefer to have our own sample holders that we can keep without that concern of activation. We've also found it extremely useful to have some alignment crosshairs. This just shows a sample box with the X, Y, and Z laser alignment on the breadboard. So alignment can be done to typically something like a millimeter accuracy in just a matter of moments. Everything is mounted on this breadboard, which is then mounted on a translation table with X, Y, and Z movement. So alignment is very simple. In addition, we have a tool that it's essentially mounting a laser on a plastic block that fits against the edges of the collimator. You can see the edges of this collimator system here. We just press the alignment laser up against the edges of the collimator, and it will show the shadow of the collimator on the test device so that you can verify the alignment of the collimator is correct. The tungsten, we have these adjustable tungsten blocks. They are 30 centimeters by 10 centimeters by 2.5 centimeters each. So the minimum thickness, and they're all 4 moved together. So the horizontal collimators and the vertical collimators can be adjusted with a hand crank. We have micrometer measurement so that a preset opening can be created.
So you got Bob on it.
And the thickness of the collimators was chosen to be able to range out 450 MeV protons. And of course, and all other fragmentation products up to 450 MeV per nucleon. So when NSRL was creating a library of beams for common usage, we selected ions of energies of 450 MeV or less that we recommend to be used, because we know that any of the fragmentation products created in the collimators will be stopped within the collimators. We also recommend that the collimators be operated as close to the device under test as possible, so that any secondary particles that are created by the beam hitting the faces of the collimators do not have a chance to scatter out and impact any of the support electronics that is not being part of the test. In addition, we have a data acquisition room that has an old BME-based data acquisition and a newer data acquisition system in a box. We have, we have a lot of patch panels with RG58 50 ohm signal cables and RG59 high voltage cables, some high speed low loss cables, and 18 Cat5e Ethernet cables. So a typical user might plug into any of these 6 Ethernet and 6 signal cables. In addition, when people are running at NSRL, we give the users a beam off switch, shown here, that just pauses the beam. It allows them to do a reset of their electronics or perhaps power cycle, and then resume the run just by throwing the switch back on. And then just an image of the patch panel, downstream and upstream patch panels. Like many of the people involved in electronics testing, we started out using an LET tool called SRIM that you are probably familiar with. Excuse me a sec.
Yeah, I mean, we can cooperate.
I have to run for just a moment. Please bear with me.
Hope everybody is enjoying the webinar. Mike already mentioned that they have an ongoing irradiation campaign. So this is a kind of a live demonstration also of how busy users can keep the facility coordinators, of course. So yeah, we will resume very soon. If you have any questions, please take note of them, because we will be collecting them, and we will try to have some round of questions at the end. So we try to have the full presentation finalized, but then anything that you are curious about, just take note, and either on the chat or directly opening the microphone, you can check with Mike about points that you might want to hear about in a bit more detail. And again, just to reiterate what Igor mentioned in the beginning, to benefit to do a bit of publicity of RADNEXT. So again, our purpose is to deliver beam time for radiation effects users overall in a broad range of facilities that cover heavy ions. Here we are talking about a very special facility with high energy heavy ions, which kind of the counterpart of this type of beam would be GSI in Europe. So if you are interested in testing with these type of beams that are being presented by Mike, but have difficulties to go to the US, or in any case would like to test in Europe, then the closest that we have nowadays is GSI, which again is a part of our network, and then we also have let's say more conventional heavy ion facilities, and also protons and neutrons. Back to Mike.
Sorry. Well, now you have a demonstration of how long it takes to do a sweep and reset the interlocks at NSRL.
Perfect, very efficient.
Thank you for your patience. So as users of SRIM, we found it a little bit cumbersome working with a tool that used units of keV and total energy rather than energy per nucleon, and it was not very friendly from our standpoint. So we used the output of SRIM to create the SRIM stack-up tool. I have an example of its use here. So you have pull-down menus to select the target material. In this case, I've selected silicon, and the ion, in this case, I've selected gold. And then you can either put in the total kinetic energy, in this case, 400 MeV per nucleon, and it will return the LET and the range, as well as some straggling information. Or you can put in the range of interest, for instance, 1.3 millimeters in silicon. So a beam energy, a gold beam of 80 MeV per nucleon will have a range of 1.3 millimeters and an LET of 36. Or you can put in the LET, in this case 70, for which you need a 21 MeV per nucleon gold beam, which will have a range of 229 microns. So this, I'll mention as an afterthought, for many of the LET settings, of course, there are two different beam energies that will give you that LET. One is above the Bragg peak and one is below the Bragg peak. So we give the below the Bragg peak energy as well, although that's never a consideration at NSRL. Also listed in the bottom right corner is the LET of the Bragg peak itself in that material. So that's our energy DEDX calculator. In addition, we added a layer that allows you to do a stack up. So I've drawn an example of a stack up here where there is an incident energy of 400 MeV per nucleon gold. And I've imagined a first layer that is 1.5 millimeters of copper, followed by 1.5 millimeters of epoxy, followed by some aluminum, some covar, and some silicon. And at each layer, it gives you the exit energy and the residual range in that material and the entrance and exit LET of that material. I'll point out a mistake that is often made when the LET is given, the entrance and exit LET, it's for that material. It's not for silicon, and unless that material that you've chosen is silicon. So in this example, after going through 4 layers of different materials, copper, epoxy, aluminum, and covar, you get to the silicon at an energy of 258 MeV with an entrance LET of 18.49 and an exit LET of 18.57. I'll note that I added another layer of silicon that is 7 millimeters thick that has an entrance LET of 18.57. Note, of course, that's the same as the exit LET of the previous layer. And then an exit LET of 47. So the LET is changing from 18 to 47 as it goes through that last piece of silicon. This stack up tool is available for download on the NSRL web pages. And we're happy to distribute it and help anyone with its use. Oh, I have a brief tour of the facility. This is showing the beam pipe, the vacuum pipe that the beam is transported in. It's a 30 centimeter cylindrical vacuum pipe, and the vacuum window is right here. And it shows the target table where people will typically mount their electronics on. And this is the SWIC, the segmented wire ion chamber, and a brief tour As you go down the rails, these are the blue things are the other ion chambers that we use for measuring the total fluence delivered. And this is some of the polyethylene that is used to degrade the beam. The big black box is the camera. And at the end is an earlier version of the pixelated ion chamber. As we go by, you can see the pixels, because this ion chamber was open to air, although we operated it at 3,000 volts. Okay, typical run. Ruben, I'm a little over time. Is it all right if I go on for another few minutes?
No problem.
Okay. So for the electronics testing, the typical experimenter will often run 12 to 16 hours per day. NSRL does not operate on a 24-hour cycle. So we shut down no later than midnight each day. And some people operate just for a single day. Others might operate for a week or more. We're currently on a program doing a three-week run for this group that are just starting up today. They might ask for 4 or 5 different ions, spanning an LET from 10 to 70. Some groups alternatively will ask for a single ion and use the degrader to span the entire LET range of interest. A typical request would be for, I would say most users would request to test their part up to 10 to the 7th ions per square centimeter total fluence. Although sometimes for the heaviest ions, the gold or bismuth, they might only want to run to 1E6. We have a variety of systems for reducing the flux, for controlling the flux. We have had people ask for as little as 10 ions per square centimeter per spill, although that would be rare. 100 is not rare. 100 to 1,000 is a common starting point, increasing to a maximum intensity in steps of 2 or 5 or 10, perhaps up to 10 to the 5th or 10 to the 6th ions per square centimeter per spill. Because it's so quick and easy to change ions and energies at NSRL, it's typical to put one part in, run through the entire ion species or energy program through a whole variety of LETs before making an access to take it out and put in a second part. So there might be 20 minutes or an hour spent on a single part, going through the entire testing protocol. The tests may be either, I would say the most common is a characterization of the part, measuring either the Weibull curve or the number of upsets as a function of LET. Although some people come and just do a pass-fail test. They want to put a flight instrument in the beam and see if it survives a 10-year flux. And they don't care why it fails. They only care if it fails. So this is an impossible to read slide, but I just wanted to show that over a 12-hour period, each of the different colors represents a different ion. In this case, the user was cycling from iron to niobium to tantalum to bismuth, spanning the LET range from 2 up to more than 30. And each one of these cycles was a different part. They would do one ion, 5 minutes later, change to another ion and another ion and another ion. Then they would make a quick access. In this case, it was about a half an hour to change the part and then go through the cycle again, change the part, go through the cycle. So it's an efficient use of beam time. Some of the groups, in order to increase the throughput, have built specialized custom circuit boards that can hold 25 chips, and they will, in a 20 by 20 centimeter pattern that will allow them to test 25 parts at once. And SpaceX was here in a 5-hour slot of beam time. They tested 300 parts. I think that's a record. Communication is key. This is a picture of the control room. This is the console that the NSRL operator sees and uses to control the beam. And we have the space in the hallway here where the testers sit. They have a similar console that allows the testers to control the beam themselves. We request that there be a single point of contact. Often you'll get 4 or 5 people involved in the test, but we want just a communication with just a single person. And we've come up with a set of recommendations. Whenever possible, I've mentioned this before, work on the plateau of the Bragg curve, not near the peak. Of course, if you need an LET of 70, there are no ions that have an LET of 70 on the plateau. So you will have to work near the peak, but we recommend working as close to the plateau as possible. In other words, use the highest Z ion at the highest kinetic energies possible that will deliver the LET that you're looking for. Combine tests of single parts with system tests. Don't delid your parts. Besides being costly and dangerous to the parts, the results that you get do not have good fidelity because the environment of the part itself is completely different. The secondaries that are produced when the ions go through the lid may have an important impact on the part test itself. Complaints that we receive. Often we, for people that want to complete their testing in a short period of time, they want higher intensity than we are able to deliver. We are well aware here that at the NASA Space Radiation Laboratory, beam time is very costly. We cost now $4,350 per hour of beam time. So, of course, when groups test here, they want to get their work done as quickly as possible. And if we're not able to deliver the flux that they're asking for, that's making their tests run extraordinarily long and making them extraordinarily costly. So that's a complaint that we frequently get. We are always working to improve our flux. Other groups have said that they would prefer continuous beam, and that's why they like working at cyclotrons. whereas the booster synchrotron that produces the beam for NSRL has only a 10% duty factor. I point out that the ions are always discrete, and if you're operating at a flux of something like 1,000 ions per square centimeter per spill, your part doesn't know the difference between 10% duty factor and 100% duty factor. But for some folks, it's a determining factor, and they will continue to work at cyclotrons for that reason. And lastly, there is more demand for beam time than there is beam time. So we are hoping to improve availability here. And one of the things that we're doing is working on a proposal to build what is essentially a copy of the NSRL facility at the accelerator next door, the Brookhaven's alternating gradient synchrotron, which will then have a dedicated electronics testing facility without having to share beam time with the radiobiologists. And we'll be able to provide somewhat higher energies, somewhat higher fluxes, and a more continuous beam spill. That proposal has been submitted. Construction would be 3 to 5 years, starting perhaps as soon as that gets funded, perhaps very soon. And that's the end. Thank you for staying with me.
Great. Thank you so much, Mike. Very, very interesting presentation, very complete.